Do you have questions about the homework?
Not yet.
Okay. Let me download it in case others. I'll, well, by popular request, now we'll have 2 quizzes.
Just two. That's what I'm quizzes.
Yeah, one Friday and another one we'll have to squeeze in towards the end.
Okay, so you're originally planning to have two quizzes.
Yeah, but we'll drop one, the lowest grade. So.
Okay. I wasn't sure if you were originally planning one quiz or two quizzes.
Yeah, originally I was planning one before midterm, one after midterm.
Okay.
All right, guys, let's get started. Does anybody have any questions on homework that's due tonight and that will be covered for quiz 2 on Friday?
Yes, question 2E.
All right, 1 second. So tomorrow, after it's due, I will post the solution. If I forget, just send me a reminder. Okay, 2E, all right. What is the writing moment? So that's this is a simple one. For small small changes in angle, you can basically use GM sine phi. For large angles, we'll talk about that today. So, but if the angle is less than 10 degrees, you can use the small angle assumption. Does that make sense?
Yes.
Yeah, so the writing moment is just related to GM and the phi angle, this angle. That's it.
I had a question on problem 2 also. What do you mean by the, you say G1, GV for G virtual? What do you mean by virtual in that case?
Yeah, okay. So in this problem, you will have a loss in GM due to the free surface that's present. Where is the free surface? Yeah, if we discharge the tank, there will be a free surface, which will lead to a loss in GM. That's basically this. The loss is G1, GV. GV is the new location. You can call it G2 or anything else. Does that make sense?
Yeah, that's what I did. I called it G2 and figured it all out like that. And I didn't know if I was just being asked the same thing the second time.
Same thing. So,
okay.
Yeah. Anybody else? Oh, didn't hear you.
Oh no, I was like, I didn't get to number 3 yet, so I don't really know what to ask for.
Oh, okay. Okay, all right. Again, if I forget to post solution tomorrow after it's due, just remind me. All right. So Okay, so we started talking about large angles, right? Everything we've done before this is small angles, 10 degrees or less. And we'll see how things change when our hull heals at very large angles. What happens to stability? All right, and let me just draw a few things here. Let's say original water line is that. And the new water line is this. Oh, I wish I hadn't done that. Okay, so yeah, that's a terrible diagram. Okay, slightly better, but not much better. So we have this volume extra submerged. We have this volume that's emerged. Okay, and we will say center of this guy is at centroid of this guy is at G emerged, and this is G immersed, GI. Okay. Yeah, this is a really, really bad diagram. I really want to start over. Okay, yeah, let me start over. This, I'm sorry, this is bad. Okay, slowly this time. Okay. Again, the proportions are not perfect. You know, the volume emerged has to be equal to the volume immersed, but fine, we don't care. All right. So for let's bring back the old sketch here. For small angles, we know the restoring torque is what? It's the restoring moment arm is Gz, and the force is delta. So in the small angle case, restoring moment is delta times Gz. Okay, this is the restoring moment arm. All right. And for small angles, we know Gz is equal to Gm sine phi, or Gm times phi. Okay. For large angles, it becomes a bit more complicated. So here we would get Gz is B0R minus B0G sine phi. Okay, it's just trigonometry. So we see this G to Z length is what? It's basically B to R minus this little part. That's exactly what's written here. Okay, then let's call volume emerged is equal to volume submerged or immersed. Let's call both of them little v. They have to be equal. Okay, and let's also call horizontal distance between GE and GI is HEHI. Okay. We're giving symbols to these things because we'll use them in something called the Atwood's formula. All right. So for small angle changes, we just had Gz is Gm times phi. We're done. But now things are a bit more complicated for very large angles. The center of buoyancy moves in a weird way, and the meta center might also move. So in this case, we won't derive it, but we have something called Atwood's formula. Which says the restoring arm, Gz, can be computed as, which is B0R minus B0G sine phi, can be computed as little v times HEHI over nabla 0 minus B0G sine phi. Okay, the main problem here comes from the HEHI. That's basically how much the centroid shifts from the emerged to the immersed part. For complicated hull shapes, you can see that's not easy to compute, especially when there's a large heel. All right. So instead of having to compute this over and over, what a designer will do is they will pre-compute the GZ. And for a given angle phi, they'll tell you the restoring arm is this much. And they'll create a chart which you can use very easily. So by evaluating HEHI and little v for various and that sort of a plot looks like this. You put phi on the horizontal axis and the one we want, GZ, on the vertical. And the plot would look something like this. Okay, we'll talk about what this plot is telling us. Okay, so let's mark a few points. O, B, let's mark this A. Right. So the designer of the hull will give you this chart, and you can use this to figure out when you will be no longer be stable. Okay. So think about this. What happens when you are 0 degrees? What do you expect the restoring torque should be? Phi is 0, meaning our hull is perfectly even keeled. What is the restoring torque?
Should be 0.
Yeah, it should be 0 because there's no need to restore anything. We are already stable. Okay? And if you push down one side, then you expect, okay, then I hope I get some restoring torque to come back to this stable position. So that's what this graph is showing us. At phi heel angle 0, we have 0 restoring arm. Okay, 0 restoring moment arm means 0 torque or 0 moment. And if we start increasing the angle slowly, the restoring torque starts increasing. Okay, and it'll keep increasing up until some point. So when you heel your ship to, let's say this is 25 degrees, that's the moment when your ship really wants to bounce back. Okay, you have a lot of torque trying to restore its state. But if you go further than this point, then you start losing that restoring ability. Okay, and then you start getting into the danger of capsizing completely. Once you hit this value, whatever it might be, let's say it's 40 degrees, what happens here? Yeah, here, once you reach, exactly, once you reach this point, there is no longer any restoring torque trying to upright your ship. So if you cross that, you will capsize. Okay, so this sort of a graph is very, very useful. This is called a curve of statical stability. Curve of
At what point did you say it capsizes at A? At point A or?
No, at B. Think about it. If you're healed and there's a little bit of restoring torque, fine, it'll still try to upright you slowly. Okay. When you're at A, there the restoring moment is the maximum, so it tries to really upright you very, very quickly. If you exceed B, then you've reached, there is nobody trying to restore your hull. So at that point, you will capsize. Okay, I'll write all of that down. So this is called curve of statical stability. I want to mark one more thing on the graph. Let me draw a tangent at the 0. Okay, and I'll tell you why I. So this point tells us G0, GZ is 0 for upright. This tells us GZ is maximum at a particular value of phi. OB is called range of stability. Because no recovery if phi exceeds B, then your ship will capsize. All right, then there's one more important thing this graph tells us. Think about you have your hull and there's waves hitting your hull from the side, or there's a strong wind from the side. This graph can be used to determine what is the maximum torque generated by this wind, sideways wind, that your hull can tolerate. Can you think about where that point might be? So the graph is telling us how much maximum wind could we potentially tolerate. Think about what happens. So we have our hull, we have a light breeze that's generating 5 Newton meter of torque. Okay, so it's trying to rotate our hull like so. If the wind picks up, it increases to 10 Newton meter of torque. Again, these are small numbers, just as example. So your hull heals a bit more. At some point, the wind speed will be so much that it'll cause the ship to capsize. Can we figure out how much torque our ship can tolerate?
Wouldn't the torque at any given phi be your displacement times your GZ on that curve? So the maximum would be, you know, where it's at A, and times your displacement and going to 0 when it gets to B and so forth.
Yeah, all right, yeah. So both of you said the same thing. Is basically this point, right? GZ maximum at A. So this value corresponds to the maximum torque that we can potentially overcome. If we if our external torque exceeds this, there's no point of return. Okay, so that the curve tells us another important thing. So GZ max tells us that if the external moment exceeds GZ max times delta, the ship will capsize. All right, then the reason I drew this dashed line, okay, the reason for that is also we know GM is GZ over phi for small angles. Okay, so for small angles, our the restoring arm GZ was GM sine phi, or GM times phi in radians. So we know that at phi equals 0, that's always when we talk about initial stability, right? We're upright, and then what happens if we kick it just a little bit for small angles? So we know this curve, it goes through all the way from 0 to maximum allowable phi. So the slope of the curve at phi equals 0 should give us exactly the value of GM. So if you compute this tangent and you find the slope, that's a very quick way of computing GM. Okay, so this curve is very, very simple but very useful. All right, then Atwood's formula used to determine this curve. It simplifies when our hull geometry is not too complicated. So for wall-sided ships, by wall-sided, I just mean the hull sides are vertical, or they look like a wall instead of being tapering down, or it's called flare or tumble home. So for simple hull shapes, as opposed to it's called flare or tumble home. Have you heard these terms before? Flare, tumble home? Yeah, I didn't know them either. So let me just pull up an image. So that's what we are used to seeing. Okay. Yeah, that's called a flare. Okay. Widest at the deck and tapering down at the keel. And the other opposite is called tumble home. Have you ever seen a tumble home hull? Yeah, and old designs, right? They used to mount the cannons over here. So that would be a tumble home design. Yeah, here. See the hull at the top deck, the hull is narrower than at the in the midsection. Okay. Yeah, so that's what the flare and tumble home refers to. So wall-sided, perfectly vertical. Nearly perfectly vertical. So for wall-sided hulls, Atwood's formula for GZ simplifies. It becomes GZ is equal to sine phi GM plus okay, this is much nicer because we don't need to compute the HE, HI, or little v. We just need to know the GM, the initial center of buoyancy, and the angle phi. That's it. Okay, and this formula gives us some very interesting things that can happen to a hull. So let's consider okay, so let's talk about when GZ is equal to 0. There's a chat. In what cases would this type of hull be more beneficial? Are you talking about a tumble home?
Yes.
I don't know. I mean, the modern hulls, the shape that we saw, that was probably for stealth. But other way, that's the what?
That's why they use it for the thumb wall was for stealth.
Okay, yeah. So for modern ships, stealth is the only reason I can think of. The flare is much better for stability, hydrodynamic performance, etc.
Okay, thanks. Just curious.
Yeah. All right. So yeah, let's consider a few different scenarios. Let's say GZ equals 0. What does GZ equal 0 mean? Is what?
It's flat.
Are you saying it's even keeled?
Yeah.
All right, we will see that's not the only possibility, okay? But yeah, that's the most probable case, right? You're even keeled. There's no need to have any restoring torque, okay? So restoring arm is 0. So this says equilibrium. No restoring torque. Okay. So when GZ equals 0, let's set this right-hand side to 0 and see what happens. Right? And when we have this, there's two possibilities. Either sine phi is 0 or the term inside is 0. Sine phi is 0 means phi is 0. And this is our trivial case where ship is upright. Okay. But the other one gives rise to a weird scenario. Tan squared phi is negative 2gm over b0m. All right. So the trivial case is there's no restoring torque if the ship is upright, or if this other situation ever arises when tan phi is equal to that. So taking this second guy, let's talk about what happens when gm is greater than 0. Mathematically, if gm is greater than 0, what can you tell me here? What solution for phi will give us this right-hand side?
B0m has got to be less than 0.
Yeah, this is saying if gm is greater than 0, meaning the top is, this guy is positive, there's a minus sign here, then b0m better be negative, otherwise I cannot have a square of anything be a negative number. So there's no real solution for this equation if gm is greater than 0. So no. Right. Which is fine. If gm is greater than 0, we expect any heel angle will give us a positive restoring torque. This corresponds to only when there's no restoring torque. Okay. Second scenario is when gm is less than 0. Let's see what happens. Negative, negative, positive on top, positive on the bottom. There are possible solutions that can exist for phi. So tan phi gives us plus or minus square root of minus 2 gm E0m. Okay, and in this case, this phi angle, this solution is called angle of Lull. L-O-L-L, not laugh out loud. Okay. So, have you ever seen, well, some of the accidents that happen, the ship will take on water, start healing, and then just stop there. Okay, that's this scenario. When it started taking on water, its stability decreased to below 0. So it started capsizing. But because of large angle, we're working with large angle changes, so it won't capsize all the way. It'll heal up to a certain point, and then stay there. That's called this angle of Lull. Let me see if I can find any images on Google. What is this? Oh, okay. It's a point of yeah, it's a stable point, but it's one where you don't want to be. It's not a comfortable, stable point. Okay, let me see. Oh no, that's list. Okay, fine. Oh, maybe that. Yeah. Okay, I don't see any nice examples, but your hull would basically be doing something like this. Okay, so it'll stay at that new Lull angle. And you can compute exactly how much that Lull angle will be. Okay, so how does this show up on our graph of
Could you call that astable stability?
astable?
Yeah.
No, I guess you would call it a neutrally, no, not neutrally.
I think that's what I meant by astable. I think there's stable, unstable, and then astable is neutral, basically.
Yeah, but neutral stability is you move it, it stays at the new place. It doesn't move either forward or backward.
Right.
I guess this would be a point of stability. Astable, I don't know. Let me draw the sketch for the statical stability curve, and then it'll become even more even clearer. So let me write a few things, and then we'll talk more about this. For GM less than 0, there are two additional solutions for phi. Remember, there's a plus and a minus, so we can heal either direction. So you heal one way is plus, heal the other way is negative, but the magnitude is the same. Okay, let's think about what the curve should look like. So obviously, when it's upright, we should start at 0. What else? There should be, our curve should hit 0 again at this phi lull. Okay, so let's say it'll come and hit 0 again here. Okay, I'll mark it later. Now, next thing I want you to think about, what should the curve shape look like? Should it start going up or should it start going down? Remember, GM is less than 0. Think about tangent and GM and curve slope. What? Yeah, you can look back to the previous curve and look at how GM is related to the tangent, etc. GM is the slope, right? Slope of the tangent. And if it's positive, we expect a straight line like so. If it's negative, we have the line like this. Okay, so our curve will look like so. The slope of this line is exactly equal to GM, which is less than 0. This angle is phi lull. And we know how to compute this. This is tan inverse of okay, and again you have your range of stability. All right, so let's think about what this curve is telling us, what's different from the other previous curve. Hull is upright, so we start at the origin. And let's say a little baby comes and kicks the hull on the side. What will it do?
Till return to the original position.
Say that once more.
It will tilt depending on the force and return to the original position.
Oh, so you're saying baby comes along, kicks it, so it'll tilt slightly and return to upright?
Yes, unless there's a super kid or something that.
All right, so that's not what will happen in this scenario. You're correct, if GM is greater than 0, that will happen. But remember, GM is less than 0, so our hull is not stable. Any little perturbation will cause you to go further.
I would say it would go further down to, would it be the minimum GZ that's less than 0?
Okay, so you're saying it would come here. And think about what negative GZ means. It's saying you don't have any torque trying to restore you. You have a torque that's trying to further imbalance you. Okay, so if you move even a little bit, you will have what's the opposite of restoring? Disturbing, destabilizing. Yeah, you have a destabilizing torque, right? This is a negative torque. So the baby comes and kicks the hull, your angle will change by a very little bit, but that's enough. Your torque is going to further destabilize you. So you'll keep tilting until, yeah, until you are exactly at phi lull. Okay, so, and that's your new equilibrium. Your hull will stay at that position. If the baby comes around and kicks it again at this lull angle, what do you expect to happen? Yeah, if the baby comes along and kicks it, tries to tilt it further, you see now your restoring torque is positive. Again, this is not torque, but you just multiply this with delta and you get torque. So you start getting positive restoring torque. So you try to tilt it further, then you restore back to this strange angle. If you try to decrease the tilt, if you try to push it down like so, what happens? Yeah, if you try to decrease the tilt a little bit and you remove it, you remove your external force, it'll go back to phi low. That's a destabilizing negative torque. Okay, make sense? It's weird, yes, I know. But this is why your job is to ensure this never happens. GM less than 0 never ever happens. Otherwise, your hull will do this. That's, that's the worst case scenario is that your hull will capsize. So this is like one point that saves you. Okay, questions? So intuitively, does this make sense? What the curve is telling us? How this relates to restoring? What happens if you impose an external tilt in a particular direction? Okay, let's do an example. We're given a ship as negative GM. This center of buoyancy is 5 meters from M. Yeah, GM would be minus 0.08. Okay, what is the angle of Lull? That's a simple formula. We don't have to think much. So phi Lull would be tan inverse negative 2 times negative 0.08 over 5. 10.1 degrees. Think about what has happened. You have a hull that is very, very slightly unstable, right? This is 8 centimeters. Negative 8 centimeters causes your hull to tilt 10 degrees, okay? So very small values of a negative stability can really mess up your hull. Okay, so any questions on that? Everybody is intuitively, you understand how to interpret curve of statical stability. Okay. All right. So from this point, we'll start discussing about, well, up until now, we've always talked about what happens if the hull is nice and it's floating, there's no damage, there's no grounding. As a designer, you have to be careful about making sure if you do get grounded, you don't fully lose all stability, okay? So we'll talk about dry docking and grounding first. Have any of you been to a dry dock? Do you know what a dry dock is? No?
Where they, you go into an enclosure and sort of like a lock, and they pump the water down, and then the boat is then suspended, by supports in a dry location, so it's out of the water.
Yeah, if you need to perform maintenance on the hull, repaint it, or de-biofoul it, you need to get it out of the water. So you basically take it into dry dock and basically pump out all the water. So, okay, so you've seen images like so, right? That's a dry dock. The ship basically sailed in, they pumped out all the water, and you can service the ship. So this is expected regular maintenance that also you have to design for. So when the water is being pumped out, you have to make sure that the ship suddenly doesn't go unstable and tilts over. Okay, and the scenario is basically very similar to if your ship runs aground, your hull, part of your hull is being supported by the ground instead of the water. So we'll talk about what happens during those during that time period when the water is being pumped out. Okay. All right. So in both these scenarios, the hull it's partially supported by an obstacle. And if you're not careful, this could lead to a loss in stability. Great. To figure out how exactly this instability happens, let's look at a sketch. Okay, so we already know G is where our weight of the ship will act. I'm not using delta here for a reason, so call this W ship. We know there will be a center of buoyancy somewhere. Let's call this B here. It has to be vertically above M. So B is here. And we get force buoyancy here. Again, not equal to delta for a reason. Okay. So in a freely floating case, those are the two main things we worry about, the weight of the ship and the buoyant force. But now there's somebody else. If your hull is touching a sandbar or a block, a support block, touching. This support creates an additional force. Let's call it P. Okay. In this case, think about what happens. What in a freely floating case, your ship floats because the weight of the ship is what? The weight of the ship is balanced by whom? In a freely floating case, the weight of the ship is balanced by whom?
Buoyant force.
The buoyant force. Now, the weight of the ship is balanced by two things. The sum of the buoyant force as well as this extra reaction support from the ground. Okay? So in this case, the displacement will be lower than a freely floating hull. The amount of water you need to displace decreases because you are getting some support from the ground. You don't need to displace as much water. Okay? So this might seem like a good thing, right? Your hull is riding higher, but it's not. It ends up decreasing your stability. We'll see exactly how that happens. So the first thing we talk about here is at equilibrium, we have the weight of the ship is equal to F buoyant plus the reaction force, which we call P. All right. For a freely floating hull, W ship we know is equal to delta, which is equal to rho seawater times nabla. Okay, and just to completely clarify this, we call this displacement, which is the weight of volume of water displaced by the hull. Okay, before we go further, does everybody here see why displacement is no longer equal to weight of the ship? If there's any confusion, you tell me. Okay, we wait for a for people to finish writing. All right, so instead of talking about ships, let's talk about human beings. When you're, let's say you're floating in water on your back, you displace a certain amount of water, okay? The displaced water weight is equal to your weight. But if a friend comes along and supports you, supports your back, you won't need to displace as much water. So that's basically the scenario. In that case, the displacement is decreased by exactly how much support you're given, right? So that's basically what we're talking about here. For a partially supported hull, the displacement is equal to F buoyant is equal to W ship minus the reaction. Okay, is this okay? Weight of the ship, part of it is resting on the ground, the other part needs to come from the water. So that's the buoyant force. Okay. So the thing that happens when you support your hull externally is the meta center moves. It changes its position. So the all right? So the supported case, meta center will move. We know we'll lose stability, so the meta center has to move down. Let's say it moves down here to a new location, M1. Okay, and we know the angle here is phi. Okay, so now let's drop a vertical from here and call this distance little a, and this other vertical, let's call this distance little b. And you see, if our meta center is the rotation, is the hinge, torque due to FB is counterclockwise, torque due to P is clockwise, and they have to be exactly equal. That's what the condition says. That's how we determine the new location of M1. Okay. So when we write this statement mathematically, this just gives us P times A is equal to FB times P, right? Clockwise moment has to be exactly equal to anti-clockwise. Okay, so A and B, we can use just trigonometry, P times KM1 sine phi. FB is W ship minus P times B is what? M1 M0 sine phi. It's just trigonometry. Km1 sine phi. Km1 sine phi gives us little a. M1 M0 sine phi gives us little b. Okay, M1 we can write as Km0 minus M0 M1. Okay, there's two things common here, P times M0 M1, P times M0 M1. So we cancel these. Right. So think about what M1, M0 represents. It represents our original position was M0. How much has it come down to M1? That's the shift in the meta center. And if we're freely floating, P is 0, then as expected, we get, there should be no shift in the meta center. With this shift, we can compute our new GM. So GM effective now is basically GM1 is GM0 minus M1 M0, which is GM0 minus P times KM0 W ship. So that's the loss in GM. So this is another thing we always want to avoid. We don't want to run aground because we will lose stability. And we can compute exactly how much if we know the amount of force being applied by the obstacle underneath. This is one way to compute the loss in stability. There's another way to do this for the same exact scenario. So let's call this method 1. So okay. Here we have considered the reduction is in km, so m moves down. There's another way to look at this, which is the g moves up. The center of gravity moves up, which we know always is bad for stability. We want our center of gravity to be low for us to be more stable. So an alternative method is called that method 2. Considers the rise in center of gravity. Okay. Why is there a rise in center of gravity? It's caused by the reaction force P. Does this make sense to you? I'm saying somebody supports you from the bottom, then your center of gravity rises up. Think of, we've talked about this in the sense of cargo loading and unloading. If somebody's supporting you from the bottom, your hull from the bottom, what is this equivalent to? Loading cargo, unloading cargo, neither. Yeah, it's like unloading cargo. You're decreasing the total weight of the hull because of this support, the seeming effective weight of the hull. So the effect, when unloading cargo, you expect the CG to go up. Same thing happens here. Effect is equivalent to unloading cargo. When we talk about the center of gravity moving up or down. Okay, we're out of time, so let's do that next class. Don't forget about quiz on Friday. Any questions for that?
Professor,
Yeah.
I had a question actually regarding the homework 4. I'm
okay.
having some issues kind of understanding or visualizing problem 3. Is there any chance you have time to do like a quick free body diagram?
Ship is floating, okay, MCTC, okay. Okay. Oh yeah, so that's very similar to what we did in class. So
Thank you.
Oh no, I can't see it while I write. Okay, give me 1 second. I have to write down the question, or basically make the sketch, and then I'll share my sketch with you. So, is the ship? We're given the draft. Okay, draft 4 is Shallow, okay. So this is 3.2 meter. This is 4.4 meter. Length is 100. LCF is given. Okay, and you put what? Weight 30 ton at 20 meter forward of amidships, and weight of what? 40 at 30 meters from 8 feet. Okay, so let me. All right, so that's the problem. Our ship is 100 meters long. The drafts at fore and aft are given. Again, always be careful. The draft value tells you what the water level is. And you add a weight. LCF is given, it's some location. Okay, weight you add. Wait, you add or subtract? Can you
I think
check the
I think you're adding. I think
both?
that's
Adding both?
I think so. Let me pull it up on my
So let's say you're adding 30 ton at 20 meters forward of midships.
yeah, you're
believe-
adding 40. So it's
I
another weight.
Okay.
You subtract 20 or
Oh,
30.
it's unloaded. Sorry, it's unloaded. It says.
Oh, okay. So unload. So you're taking off weight, right? So 30 Newton, 20 meters from midships. So you know where to place it, and you're unloading it. Same thing here. You're unloading 40 ton from 30 meters from aft. So over here, okay? When you know these two forces, you can compute the total moment about the LCF.
My only question with this problem is when you're doing the net change in moment, which was the first part, when you're doing it from the midship, it says 20 after the midship. Are you adding so it's 50 plus 20 times the ton of the load, or are you subtracting it from the length? Because I know when you were doing that, you were doing you were talking about forward from the AP. So what you would do is you would find the distance and subtract it from the meters that you're given and multiplying that by the tons during the example in class.
Okay. You're confusing yourself. It's simpler. Always you have to compute moment about the LCF, okay? So
Gotcha.
you always need to find this distance. Whether you subtract, add, that's easy, right? So always moment about the LCF, okay? Whether you give a positive sign to the moment or a negative sign depends on whether it's clockwise or anti-clockwise. So here it seems we will have opposing moments. So one will get a negative sign, the other will get a positive sign. Okay, make sense?
Yes. Yeah.
All right, anything else? All right.
Thank
So,
you.
Sure.
Thanks.
See you guys Friday. Don't forget about quiz.
Mm.